In this video we're going to talk about the arrangement of electrons in orbitals, subshells and shells. What you remember from earlier lessons and from GCSE is that the electrons are arranged in shells. The maximum number of electrons per shell is 2 electrons for the first shell, 8 for the second shell, 18 for the third shell, 32 for the fourth shell. We have seen that the reason for this difference in numbers is because of the number of subshells available. So the first shell has only one subshell, the second shell has 2 subshells, the third shell has 3 subshells, and the fourth has 4 subshells. The rules and principles arising from quantum mechanics are the Heisenberg's uncertainty principle, Pauli's exclusion principle, the Aufbau principle, Hund's rule of maximum multiplicity. So the first two rules give us our definition of what an orbital is. The third principle, Aufbau principle, tells us we must put electrons in the lowest available energy level, and the Hund's rule, when in orbitals of equal energy electrons will try to remain unpaired. That is what I call the sitting on a bus rule. Okay, and so if we put together the Heisenberg's uncertainty principle and the Pauli exclusion principle, we get our definition, which was an orbital is a volume of space which can hold up to 2 electrons with opposite spin. And here are the shapes of some of the familiar orbitals. So a spherical for the S subshell, the P subshell is dumbbell shaped, and then we've got these double dumbbells for the D subshell, and then the dumbbell with the collar. So we put our electrons in the lowest available subshell or energy level, because that's the Aufbau principle. Okay, but the quantum shells get closer together in space the further away from the nucleus you travel, and there is in fact an overlap of the energy levels of the 3D and the 4S subshells. And so this is what actually happens, is that the 4S subshell fills before we put electrons in the 3D subshell. And we see that because when we're thinking about the periodic table, the S block and the fourth period, or the fourth energy level, comes before the 3D electrons, or 3D elements, should I say. Okay, so the order of filling the orbitals. Okay, just set that. Okay, now, a couple of ways you can remember how to do this. One is the arrow method, where you write lists of the different subshells. So the S is in one column, the P's are in another column, D's are in another column, F's in another column. And so what we do is draw parallel arrows saying we fill the 1S subshell first, we then fill the 2S subshell, we then fill the 2P subshell, followed by the 3S, the 3P subshell by the 4S, the 3D followed by the 4P, the 5S, and that is as much as we need to know for A level. But then beyond that, it would be the 4D, the 5P, the 6S, and then the F block elements become involved. Okay. So the way we represent our electrons using this box filling method is to use arrows. Typically it's half-headed arrows like these ones here, and we represent the opposite spin by having an upwards pointing arrow and a downwards pointing arrow. We've got the colour coding here, kind of the pink for the s orbitals. The p is a lime green, and then the d is a slightly darker green. Okay. So here's an example of hydrogen. Hydrogen, we follow the Aufbau principle. We put one electron in the lowest available energy level, and so we have an electron here. When we go to helium, we put the electron in the lowest available energy level, which is the 1s subshell, and we must apply Pauli's exclusion principle, which is the electrons must have opposite spins. So we represent our second electron having a downwards, pointing downwards. When we get to lithium, because the first shell is filled up, we must go to the second shell, and the lowest available orbital is the 2s. So we put one electron in there. And then when we look at beryllium, the second electron to go into the second shell must go into the 2s orbital, because that's lower in energy than the 2p. And again, we have an upwards pointing arrow and a downwards pointing arrow to represent our electrons with the opposite spin. Then we go to boron. We've now got 5 electrons. The 1s, the 2s are completely filled, so we've got to go put our first electron in the 2p orbital. But there are 3 p orbitals here. Now the next electron, so in carbon, which has 6 electrons, it does not pair up with the first electron. It goes and occupies another orbital, to minimise the repulsion between the electrons. And what I said earlier was, this is the sitting on the bus rule. So imagine you get on a bus and you see that the seats are singularly occupied or empty. You go and sit on an empty seat. You don't go and sit next to a stranger. Okay. And then we follow this through for the next element, which is nitrogen, and we put its electron in the third p orbital. Okay. So again, we're minimising any repulsion, making it lower in energy and therefore more stable. Oxygen now, we have a paired up electron in our 2p orbital, and whilst there is that repulsion between these electrons, it is minimised because of the opposite spins. And we'll cover in a later video the explanation for this. Okay. Then we get to fluorine, which has got 2 paired electrons in the 2p, and then neon, which has got all electrons in the 2p subshell paired up. Okay, and then if we go through sodium to argon, then what we can see is that these electrons fill up. So sodium puts 1 electron in the 3s subshell. Magnesium has 2 in the 3s subshell. Aluminium, silicon and phosphorus have singularly occupied orbitals here. And then we get to sulfur, we start pairing up the electrons. And so this represents argon. Then we get to potassium, and potassium, because puts its electron in, its last electron in the 4s orbital, because it's lower in energy than that of the 3ds. Similarly for calcium, pairs it up, and then when we get to the D block elements, we then start filling up the 3D elements. Okay, and that concludes the video for today, and we'll cover different aspects in class. Thank you for listening.